Okay, it is time to make the integral test official. What is it all about? How do you do that? It's not my favorite test to run because you have to, first establish that the hypotheses are held for a particular problem, and then you have to run an improper integral, and sometimes that's not easy. But what's really cool about it is you get this nice picture. We did this in another lecture where, for instance, if we're looking at the so-called n is 1 to infinity, 1 over n, the so-called harmonic series. I don't know if you watched that video or if you read it in the book, but you got this series. That's the function f of x, pretend is 1 over x. But embedded within it are these points, if you will, of the series n is 1 to infinity, 1 over n. And I was doing this game of, hey, these rectangular areas that I'm creating are 1, 1/2, 1/3, because the base is 1, 2, 3, 4. The base width is 1 and the height is 1. Here the base width is 1 and the height is 1/2. So when you go base length times width, or whatever you want to call it, you get these areas. And if we add them up, we find that they're actually greater than if we were to integrate from 1 to infinity, 1 over x dx. Now, when we do that integral, we have this visual of the area under the curve. Okay, and if the area under the curve is infinite, which it is, we found out, this is actually the natural log of x from 1 to infinity, which is divergent. So if the area under the curve is infinite, the area in the rectangles is infinite. So that implies, this argument implies that this series also is divergent. It goes to infinity. It's unbounded. Okay, if you were to look at its sequence of partial sums, S1 is 1, S2 is 1 plus a half, one more, S3 is 1 plus 1/2 plus a third. You keep adding numbers to it, but the numbers are still so-called fat enough or big enough for the sum to just kind of creep towards infinity slowly. Okay, in fact, the speed of growth of the natural log function kind of gives you the feel of how quickly the sum does creep to infinity, but to infinity it does go. I'm going to break this series, this particular section, up into two videos. One, we're going to focus on the so-called p-series, which are hugely important to us in our homework and on the test and in Calc 2 in general. But then I'm going to do one example on another video, a shorter video. Just here's an example of doing the integral test again. If you run the integral test, okay, if I ignore for now, I'm going to ignore for now these statements that what has to happen. Let's look at them, though, very quickly. Okay, I'm not ignoring them. The terms have to be positive of any series. Well, pretend we're looking at this picture right here. Obviously, the terms are positive. The terms are decreasing, 1, 1/2, 1/3, 1/4, pretty clear. And they're going to 0. Yeah, and in this case, you might do the lim as n goes to infinity. 1 over n is definitely 0. It goes to 0. So they're shrinking to 0. That's the hypothesis for the integral test. You can't have negative functions. You can't have terms that are positive, then negative, then all over the map. And of course, you can't have them not go to 0 because that breaks the divergence test story, right? So it kind of makes sense, but the positive part, you cannot have the curve dipping to the negative infinities, okay? So we're trapping this thing in a way with our hypothesis. So if we just kind of pay lip service to it right now, let's discuss the p-series. Because, again, when we run the integral test on these guys, 1 to infinity, 1 over x squared dx, do you see what we did? Is we take that series and we let, like, f of x equal 1 over x squared. The series is adding up 1 over n squared. So we're going to look at the function, the integral of 1 over x squared. What would we do here? Well, we'd let f of x equal 1 over square root of x. And so we would be looking at the integral from 1 to infinity of 1 over the square root of x. So these are the two guys. We're going to reach a conclusion and say those are your p-series, and whenever you see them, you know what happens. So I'm going to integrate these guys really quickly to see what happens. I want you to remember that this one here, if we did the integral 1 to infinity of 1 over x dx, we've already done it. This guy diverges. It's unbounded. It goes to infinity. Okay. These are like sister functions, if you will. In this case, we're integrating 1 over x squared, which means we're really integrating x to the negative 2, which means we get x to the negative 1 over negative 1. Another way to write that is minus 1 over x. We are going from 1 to infinity. Over here, same story, very similar. That's why we're going to just memorize these things. Don't want to do these over and over again. This is the integral of from 1 to infinity of x to the negative 1/2 dx, right? So when we integrate that, we get x to the 1/2 over 1/2. How about we write 2 square root of x from 1 to infinity? I want you to notice what happened. Okay, watch what happens here in this case. We plug in the upper limit, we get minus 1 over infinity, so to speak, minus a minus plus 1 over 1. What about that 1 over infinity? Like you're saying, well, it's going to be 1 over b as b goes to infinity, right? The limit. Well, this guy goes to 0. He shrinks to 0. And we have 1, which means it converges. That means, in our case, we have a picture that looks like this, 1 over n squared. That's 1 over x squared, let's say. And now I'm going to do a little trick to you guys. I'm going to tuck these guys underneath like this. So this could be 1, but then this would be, the height of this guy is, this is 2, so it'd be 1/4, 1/9. And if you add these guys up, they are actually less than the area under the curve, but the area under the curve is 1. So our sequence of partial sums converges. Okay, so the integral test is just basically saying if the improper integral converges, this implies that the series 1 over n squared, n is 1 to infinity, also converges. So the gist of the integral test is whatever the integral does, the series does. Whatever the integral does, the series does. We don't know much about the series, but we know how to take integrals, and that's how this is done. Look at this guy over here. This time we get 2 square root of infinity minus 2 square root of 1. Do you notice something? This time, this thing is going to march off to, it's unbounded. It is divergent. It diverges. So the integral test says what? Whatever the integral does, so does the series. So that implies that the series n is 1 to infinity, 1 over square root of n also diverges. See, the game for us is to tell the world, hey, I figured out this guy converges. I figured out this guy diverges. But there is a real cool pattern here, and we call these things p-series. Okay, the pattern is this. Looks like I can write it down below, so I will. So, p-series. Did you notice the format of these guys? N is 1 or 2, or who cares where it starts, over to infinity. And it's a 1, or it could be a 5 or any other number over, but the main thing is down here. In fact, I'll make this a different color. N to the p, okay? Where p is a power of n downstairs. Well, we noticed right here, we're looking at the series 1 over n to the 1. P is equal to 1. In this case, 1 over n to the 2, and over here, p is equal to 2, p is equal to 1. In this case here, p is equal to 1/2. Okay, so what we ended up with is converges, diverges, because it's harmonic series, and down here, diverges. How can you tell what is going to do what? Okay, this guy is a p-series, and they converge. If p is greater than 1, they diverge. If p is less than or equal to 1. Now, p is a positive number, so really you could say 0, on the back end. But that's the story of p-series. If you ever see one, you can tell the world straight off, whether it converges or not. Okay, it's the integral test. Every time we integrate, the power goes up by 1. But if you're x to the negative 2, you bump up to x to the negative 1. And that means it's 1 over x. And when infinity's plugged in there, you go to 0. But if you, in this case, are 1/2, if the power of x is negative 1/2 and you integrate, you go to plus 1/2. So you're less than 1, you're going to integrate to greater than 1, and you're going to be integrate to a positive value, and you're going to diverge. So that's the cutoff right there. Here's another example, and we'll turn off this particular tape. If I gave you a series n is equal to 1 to infinity, I put a little number up top, and then I go, oh, it's the cube root, say, of n squared. And I say, does that converge or diverge? Oh, I better run the integral test. And I say, no, you don't. No, you don't. Instead, what you do is you go, well, I can take out the 5. Did you know that? N is 1 to infinity. 1 over, and then I switch that power n to the 2/3 power because I know algebra. Okay? Anytime you have a number in there and you don't want to have it there, you can move that 5 out just like you're integrating. But in this case, what you say is, you know what? I see a p series with p equal to 2/3, and 2/3 is less than 1. And remember what that says right here. That implies the series, what? Diverges. It's a one-liner. You just look at that and you go, it's a divergent p series. That's how smart you're going to be after studying this a little while, okay? That's our first, and then I have one example of a harder kind of integral test on the next tape. All right, I'll see you later. Thanks for watching.